Stoichiometry is an area of chemistry that deals with the quantitative relationships between a reactant and a product, or reactants and another reactants, or a product and a product. So it deals with everything that is related in a chemical reaction. So the key term here is quantitative, and what does quantitative mean simply other than we are dealing with math? Stoichiometry is important in a practical sense because in a chemistry lab, you need to know how much of each reactants to add into a reaction in order to get a product and not waste all those reactants. Or you can use stoichiometry to predict how much product you will get based on the reactants you are adding together. Let's take a real-life example, a very simple analogy. Just like in a cooking recipe that says for every 1 box of brownie mix you have, you need 2 eggs to make a tray of brownies. So stoichiometry would help me decide how much of each ingredients to add to make this brownies. Let's say I want to make only 1 tray of brownie, and I already have 2 eggs in my fridge. So when I go to the supermarket to buy my brownie mix, how many boxes of brownie mix should I buy? Right? You just need 1. So stoichiometry is a way of accounting what reactants or ingredients you need versus how much product you're going to get, how many trays of brownie you're going to make. Now let's bring that analogy into the chemistry world. One famous example of a reaction is this reaction called the Haber process. To briefly introduce you to it, it's a process where you take nitrogen gas in the atmosphere, right? And hydrogen gas also in the atmosphere, and you combine them together to make ammonia, NH3, also a gas. And this ammonia was very important back in World War I. But in any case, we're just going to use this as an example of stoichiometry. So in a chemical equation, there are many parts, and we already talked about this, but let's review, right? First of all, in the parentheses, it tells you the state of the matter, not important so much in today's lesson. The other 2 parts are the chemical components themselves, right? For example, the N2, right? So it says this compound has 2 nitrogens in it. H2, this compound contains 2 hydrogen. NH3, this product compound contains a nitrogen and 3 hydrogens. Lastly, a third component in a chemical equation that I want to draw your attention to is the number in front of the compounds themselves. In this case, you mainly see 3 in front of hydrogen gas and 2 in front of ammonia. There's also a hidden one, 1 in front of nitrogen gas. Remember in chemistry, if there's a 1, we usually don't write it because it will be assumed to be there. Okay, so what are these numbers called? They are called coefficients. So coefficients is just like in a recipe, tells you the quantity of each component in order to create a product. So in this example, on the simplest molecular level, it means in this case, you need 1 molecule of N2 and 3 molecules of H2 to give you 2 molecules of ammonia, NH3. So in red, you can see I have 1 molecule of nitrogen, which has 2 nitrogen atoms in it, and I have 3 molecules of hydrogen gas. Each hydrogen gas molecule has 2 hydrogen atoms. When they combine and they react together, they will form a new molecule, ammonia, NH3. So you can split it up like that if you want to have a visual representation of that. And the other nitrogen is going to combine with the other 3 hydrogens. Right, so that's on a molecular level. The coefficients tells us the relationship between the quantities of the reactants and a product. In this case, a 1 to 3 to 2 relationship. Whether that be 1 to 3 to 2 of molecules. So this is just the ratio, right? The ratio can always be magnified. For example, 1 to 3 to 2 is the same ratio as 10 to 30 to 20, or 100 to 300 to 200, right? So let's extrapolate that into the mole sense, right? 10 to the 23rd, there's going to be more than 1 molecule, more than 100 molecules. There's going to be an Avogadro's number of molecules, most likely, or even more. Right? It's more convenient to speak of this in terms of moles when we're talking about molecules. So the coefficients gives us what we call the mole ratio. So for every 1 mole of nitrogen gas and 3 moles of hydrogen gas, you will get 2 moles of ammonia gas. And from the mole ratio, you can write many relationships. For example, in this chemical equation, what is the relationship between nitrogen gas and ammonia gas? We see that for every 1 mole of nitrogen gas, you will make 2 moles of ammonia, right? So the relationship there is a 1 to 2 relationship. So how can we write that? So 1 mole of N2 over 2 moles of NH3. Again, any conversion factors can be inverted. You can write the inverse of this, and it will give you a second conversion factor depending on your unit analysis, your dimensional analysis. So you can also write 2 moles NH3 over 1 mole of N2. Okay, so that's one pair of relationship. What's another pair? You can also relate hydrogen gas to ammonia, right? So what's the relationship there? It's a 3 to 2 relationship. Again, that or the inverse of that. All right, is there another relationship we can write? Remember, you can write any compounds. It doesn't have to be a reactant to a product. It can be also a reactant to a reactant. So in this case, what is that? It is going to be, right, you have nitrogen and hydrogen. Their relationship is a 1 to 3 relationship. All right, so we have all the relationships we can from looking at the mole ratio. So looking at this conversion factor, it is relating moles of something to mole of something else. So whenever you need to convert between a mole of one thing to mole of another thing, you would always use the mole ratio. Let's do an example. So this example reads, how many moles of ammonia is produced if 4.20 moles of hydrogen gas are reacted with an excess of nitrogen? Okay, so let's dissect this example, this question first. I want to first cue you into the word in excess of nitrogen gas. So that is to cue you in to tell you that nitrogen gas will not be considered in this question, okay? Because it is in excess. We don't care about it. I'll talk a little bit more about this in the next section when we talk about limiting reagents. All right, the next thing I want to dissect is to always label what is your given and what is your needed, right? So what is the question asking you to obtain? It's asking how many moles of ammonia, right? So moles of ammonia would be your needed. So your unit at the end should be in moles of ammonia. And what is your given? Your given is the situation it is in, which is that you have 4.20 moles of hydrogen gas. So I'm going to label that as my given with a G, N was for needed. So like in any conversion factor problems that we have solved, we start with the given, you multiply a conversion factor until you get what is your needed. So let's start with a given. So in this case, we're going from moles of something to mole of something else. A perfect example where we should use the mole ratio. And what is the two things that we are relating to each other? We are relating ammonia with hydrogen gas. What is their relationship? A 3 to 2, right? Now, remember we said for every relationship we can write 2 conversion factors. So which conversion factor do we want to use? Right, you want to use the conversion factor where H2 is on the bottom as a denominator so that the H2 can cancel out in unit analysis. Right, so unit or dimensional analysis says moles of H2 cancels out, leaving us only moles of ammonia, which is what we need. So perfect. Doing the math, we would get 2.80 moles of ammonia. Now notice that you need 3 significant figures because in your problem, it's given you that you have 3 sig figs here. The number 2 and 3 are whole ratios, so they are not a measured number, so no significant figures. So let's do a checkpoint question now. Propane fuel, C3H8, is used in barbecues. How many moles of oxygen gas are needed to react with 1.6 moles of propane gas, given the equation below? We know that for every 1 mole of C3H8, how many moles of oxygen do you need? You need 5 moles of oxygen, right? So that's our equality. That's going to be our conversion factor. We are given that we have 1.6 moles of propane gas. So we just need this conversion factor to tell us how many moles of oxygen we get. Again, this would be 1 mole of propane gas to 5 moles of oxygen. Doing our unit analysis tells us we are going in the right direction. So 1.6 times 5 will give you 8.0 moles of oxygen. Answer C.